Hi and welcome back to another LeetCode video. We're looking at LeetCode 322 coin change, which is a medium one-dimensional dynamic programming problem. So it should be easy for us to solve if we know the basic of dynamic programming. I'm just going to walk you through a very simple solution that I think is easy to understand and should be very easy for you to implement as well. So let's understand what we are dealing with here first. So we're given an array of coins that contain the different dominations of coins. And we're given an integer value amount, which represents a certain monetary amount. And the goal is now to pick coins using the dominations that we have in the coins array that sum up to the amount. And we're allowed to pick different coins multiple times. So here's an example. We have the coins with values 1, 2, and 5 available for us. And we should try to pick the fewest amount of coins that sum up to the total or to the target value of 11. So one way to do that would be to pick coin 1 11 times, right? That would sum up to 11. We could pick the coin 2 5 times and coin 1 1 time. That would sum up to 11. But we can also pick the coin with value 5 2 times and then pick the coin with value 1 1 time, which is the correct solution, which is the shortest or the smallest number of coins, of different coins that we need. Not of different coins, I misspoke. Smallest number of coins that we need to build a sum that sums up to the target amount. Here's another example where we just have a coin that has the value 2, but we need to find a combination of coins that sum up to 3. Obviously, that's going to be impossible. So in this case, we're outputting -1. If we're trying to build an amount of 0 and we have any coins available, that means we don't need to pick any coins. We already have that amount by not picking any coins. So the output will be 0. We need 0 coins to build this amount. Right. So that is everything we really need. And now, if you remember with dynamic programming, we're trying to find a way of building up the final solution from solving subproblems. We're also looking for overlapping subproblems so that we can use previous smaller subproblems to construct the solutions for larger subproblems until our subproblems become so large that they're essentially the solution to the entire problem. Kind of the gist of dynamic programming. And the way we're going to deal with this is, well, let's say we start with an amount of 0, right? We start with that amount, and maybe our target amount is, let's say 11. Let's just pick the first example. And we want to get to the target value of 11. Well, if we have 0 amount, what are our choices? Well, we can pick any of those 3 coins, right? So we'd say, okay, let's increase our amount by 1, which means we picked 1 coin, and now our amount is 1. We can then decide maybe, I don't know, maybe we pick coin with value 5. So now we're getting to 6 and we've picked 2 coins. And now we're at 6. Maybe we decide to pick the coin 2 next. So we get at 8 and we pick 3 and so on and so on. And then finally, we might reach the target amount and a certain number of coins that we have picked. And well, we need to explore all the different ways of how we can pick coins and then choose the one that has the smallest number of coins in it, right? And well, that is kind of the intuition. Now, dynamic programming exploits different exploits the fact that if we try to build all of these different paths to reach the amount, it's going to be an exponential growth, right? At every amount, we have a lot of possibilities to choose what the next amount is, right? Depending on the length of our coins array. So what we really want to do is, we want to avoid recomputing. Let's say if there's another path to get to the position where we have the amount 6, right? We could pick 1, but 6 times, and then we would also reach maybe the amount 6, but we have now, well, we have picked 6 coins along the way. So we want to remember what is the minimum number of ways to compute the different ways to reach that amount. And we don't want to recompute it, right? So dynamic program is going to exploit that, and by doing so, going to reduce the amount of calculations that need to be done massively. Typically, the way you do that is, well, you can do it in an iterative way. I like to do it in a recursive way where we say, okay, let's define a helper function that formalizes this recursive relationship of when we know the value of how to get to 11, how many different ways are there to get to the value 8, and then how many different values are there to get to the value 6. We build up the solution. So what we're going to do is we have formalized this as a recursive function in the following way. So we're going to give this function the amount of change that we have, and this function should return us how many coins do we need at the minimum to get to that amount. So that's what we'll do. We just pass in our amount into that function, and then we let the function handle the details. Well, so the base case is, well, what we've seen below here. So if change equal to 0, well, we don't need to pick any coins, right? We just return 0. So this case will terminate our, I guess, the recursion. Now, in the case that we still have change that we need to, I guess, figure out how to get that amount in the fewest number of coins, well, how do we determine it? Well, we're going to try out all of the coins, right? So for coin in coins, right, we're going to check if the current change minus coin is still larger or equal to 0. If it's below 0, then it's not a possible solution and we can't pick it. But if we can pick it, what we could do is we could say, okay, let's call our recursive function. This is now where our the relationship to recursion comes into play. We're going to pass in the value of c minus 1. And because we make a recursive call, it means, and we have picked a coin here, we're picking this coin, we have to say number of picked coins is that. Right, so now we have to initialize our result variable, but if we want to return the minimum number that we pick, we probably have to say result is the minimum of the current result and whatever this recursive call gives us. Because it might be that when we pick different coins, we get a different minimum number of coins that we need to get the remaining amount, which is change minus coin. And so we're going to say, okay, well, since we're taking the minimum here, we want to make sure that in the beginning our result is infinitely large. And you can do this with float infinity in Python. And then in the end, you just return the result. And finally, what you also need is, well, you need to check whether, if that is, if the return value is infinity, then we should return -1, right? So we don't want to return infinity in that case. So we return result or -1, depending on whether results is. So what this does is we have an array that contains the result and -1, and this is the expression that selects the index. So if this comparison is false, it will pick the first one, and if this is true, it will pick the one at index equals 1. And so that'll do that for us. Now, I talked about how we want to remember the results of our the intermediate results, and the way to avoid deep duplicate calculations of the DSF helper function is, well, we can use a cache for that. And why not define our cache ourselves like so? There are two ways to do that in Python. You can just use a cache decorator, but you can also just define your own cache, and then what you do is if change not in cache, well, then you need to go through the calculation, and otherwise you just return the value that you've previously computed. So you could cache change, And you also have to, of course, update the result here, right? So you say cache change equals result here, and what else? And the base case, we can actually move this into our cache as well. So if I try to look up the change of 0 in the cache, then the result is going to be 0. So now we've moved the base case into our memory as well. I'm going to be happy by that. Right, so now let's run this, see if I made any coding mistakes along the way. Change. So now, of course, I made one. And let's see, what else do we have? Name C is not defined, right? That's because it's spelled coin, not C. Right, so this is so this passes the 3 test cases that we went over first. Now, if I submit this again, we see that it passes all of the tests, and yeah, that's all there is to it. So it's pretty straightforward. You just so what could throw you off is that you know, the length of the coins array is much smaller than the what the amount could be, right? So, but we're still creating essentially a memory for all the different amounts that we have. So if we look at the space and time complexity, what we'll have is space. Let's say n is the, oh, what should n be? Well, the amount, right? And m is going to be the length of the coins array. So if we look at our recursion, because we're using memorization here with the cache, it's guaranteed that we're never going to run our recursive function more than exactly n times, right? So it's n times something, namely the effort of running the function. And here, that runtime is dominated by iterating over the coins array. So we actually have an n times m time complexity, and in terms of space, we also have a space complexity that's linear in the amount, which can be quite large, but that's pretty much the space and time complexity that you have for this problem. And that ends the video.